Welcome to Hidden Layers, where we explore the people and the tech behind artificial intelligence. I'm your host, Ron Green, and I'm delighted and honored to have Dr. Raymond Mooney joining me today. Dr. Mooney is a luminary within the field of artificial intelligence. He's been at the forefront of its evolution, where he's witnessed and contributed some of its most significant transformations. Today, we're going to discuss some of the enormous changes he's witnessed within the field over his career, reflect on the shifting challenges of the field, and discuss the future trajectory of AI in research, education, and its impact on society. Dr. Raymond J. Mooney is a professor in the Department of Computer Science at the University of Texas at Austin. He received his PhD in 1988 from the University of Illinois at Urbana-Champaign. He's an author of over 200 published research papers, primarily in the areas of machine learning and natural language processing. He was the president of the International Machine Learning Society from 2008 to 2011, program co-chair of the Association for the Advancement of Artificial Intelligence, general chair for the Human Language Technology Conference on Empirical Methods in Natural Language Processing, and co-chair of the International Conference on Machine Learning. He's a fellow of the AAAI, ACM, and ACL, and his work has been recognized with multiple prestigious awards, including a Classic Paper Award and several Best Paper Awards at leading conferences across artificial intelligence, machine learning, and computational linguistics. Ray, thank you so much for joining us today. I'm really excited about this conversation.
Okay, well, it's great to be here to talk about the amazing changes that have been happening in AI lately.
Yeah, it's really remarkable. Let's start off. Let's go all the way back to the beginning. I know that you became interested in artificial intelligence back when you were a senior in high school. It was a very small field back then. What was it that attracted you to AI in the first place?
Yeah, so I think like a lot of nerd kids, I was into watching a lot of science fiction, both reading and watching TV. And I guess sometimes I always mention Lost in Space, right? For those who remember that from the 60s. And there was Will Robinson, and he had his robot, who was like, warning, warning, Will Robinson, aliens approaching, Yeah. So, I was a sci-fi kid, and I always wanted a robot. And so it was a natural attraction to me. I read a lot of science fiction, Arthur Clarke, Asimov,
right.
Heinlein, all the, Herbert. Of course, Dune I'm waiting to see Dune 2, right?
Oh, I just saw it. Fantastic.
Oh, okay. And so, I was a sci-fi geek kid. And so it was just obviously a topic that attracted me. And then, so I actually took a programming class in senior in high school, which I guess at that point it was 1979. Wasn't that common? It was on a teletype with paper tape. There was any idea what that means. And you had a dial-up modem,
Yeah.
And that's where I started.
Okay, that's fantastic. The field has really evolved over your tenure within it. And part of the reason I'm so excited to chat with you is I don't get the honor of talking with people who've worked in AI very often who've been in it longer than me even. So what are some of the biggest changes when you look back, and you think back about the 80s and 90s, what were the biggest changes over those couple of decades that you remember either being excited about or thinking were maybe movements in the wrong direction?
Yeah. So again, AI has gone through a lot of different eras in its history. And so the era I grew up in is sometimes called like the rule-based or logic-based or expert systems era of the 1980s, where the way you built AI systems was, human engineers sat down and tried to write rules in a logical language that described the knowledge of the domain. Say you're doing medical diagnosis. The AI expert would talk to a doctor and say, okay, what symptoms indicate this disease? And then you'd type in some logical rule, establishing that. And then you would run this inference engine that would use those rules to make conclusions about, say, a particular patient or a particular case. But then, people started thinking, well, it's really a pain to have to handcraft these rules. Can we actually learn those rules from data? So that was sort of the original origin of machine learning, at least from my perspective, is how can we build algorithms that look at data and learn the rules behind it automatically from the data rather than having to have the human, so quote, knowledge engineer, type in that information. And so that was the original era I was brought up. And then while I was in grad school, the neural nets became a big thing. So I think we talked before that neural nets has a very old history. It really started in the 1950s with Rosenblatt's perceptron algorithm from the mid to late 50s. Right. But then it went into sort of hibernation, I guess you would call it, when the rule-based paradigm came up, because Minsky and Papert wrote this book in the late 60s saying perceptron's very limited, it can't do very many things. And they promoted, Minsky, of course, was one of the big ones, and John McCarthy, promoting the logic symbolic-based approach to AI that was dominant when I started in the field. But then neural nets made a resurgence in the late 80s, the origin of this approach called backpropagation, where you can train 3-layer networks. Instead of just one neuron, you could actually train 2 layers of weights with this algorithm called backpropagation. And it was demonstrating, successful performance on a number of tasks. And so that was I would call that actually the second era of neural networks.
I totally agree.
And that was dominant when I was sort of transitioning from graduate school into being a faculty member here at the University of Texas. And then it's sort of the limitations of those simple 3-layer networks came about, and it was hard to train deeper networks. Everyone realized, even from back in the 60s, the Perceptron book talked about how, it'd be great if we could train really, really deep neural networks, but we didn't have the algorithms nor the data needed to do that. And so the 3-layer network sort of era sort of plateaued. And then other techniques took over, like Bayesian reasoning and probabilistic and so-called kernel methods and support vector machines. And there we're getting our way through the 90s at that point where, that was dominant for a while until our recent era of deep learning, where people just started trying to train deeper networks. Some new algorithms came along to help learn deeper networks. And also, the biggest change is lots of data, right? We now had, thanks to the internet, there were tons of data out there that we could train these models on. And now it became successful and possible to train much deeper networks. And then that led to our current, quote, deep learning era. And do I think there were ever mistakes along this whole route? I wouldn't say so. I think, the field has tried different ideas over time, and each idea has its own, strengths and weaknesses. And I think, that's true of even our current deep network model today. But I think the field's been making constant progress in a lot of ways over that entire period, even though it's been a bumpy, very multi-paradigm road.
When did you kind of shift your focus away from rule-based systems? You probably started exploring machine learning a little bit. When did you feel like you were going to move really heavily towards machine learning and move away from rules-based systems?
Yeah, so I really started as a machine learning person. So my thesis advisor, Jared Young at the University of Illinois, had done hand-built language processing systems. He was building these things called scripts, were sort of knowledge of events. So the idea was from Roger Schenck, his thesis advisor, who got his PhD here at the University of Texas in the late 60s in linguistics, was a very early influential figure in the area of natural language processing. Mm-hmm. And his students in the 70s built these systems where it's hand-built knowledge bases. And Jerry, particularly my thesis advisor, built this system using scripts, which are sort of sequences of events. The classic example that Schenck always used was restaurant. So how do I understand a text about a restaurant? So the classic example, a story, you get a story like, John went into the restaurant, he ordered a steak, he left a tip and left. And then you ask the question, what did John eat? It's like, I never mentioned that he ate anything. I said he ordered a steak and then he left a tip and he left. But if you know about what happens in a restaurant, you know that why do people go to restaurants? Because they don't order stuff and then leave a tip. And of course they ate it but that we know that as humans, but the computer doesn't know that, right? So you had to hand code this so-called script, which says, here's how a restaurant works. You go into it, you get the menu, you talk to the waitress, you order something, they bring it, you eat it, you pay, and it has all this knowledge about what happens in particular events. So for his thesis at Yale University, my advisor had handwritten these scripts with his knowledge about all these events, and he actually connected it to the API Newswire and could understand news stories, interpreting it with this sequence of events so he'd have like an earthquake script. And goes, well, here's what happens in an earthquake. So then it could read an article about an earthquake and understand it better and fill in the gaps that weren't explicitly mentioned, which is what a person does when they read something. But he was tired of building these scripts by hand. So he came as a faculty member to the University of Illinois saying, I really want to be able to machine to learn these scripts automatically from data. And he took me on as a new grad student with this vision, and I tried to execute on that. And we worked on this approach called explanation-based learning. We actually learned from just one example. So I built my thesis system, learned a script or a so-called schema for kidnapping by reading one story about kidnapping that was very detailed and then understood how kidnapping worked and how the actions that the people were doing helped them achieve their goals. And it would then learn a script from one example by so-called explaining that example and generalizing it into a general knowledge structure that it could use to understand other stories. So I really came into the field, thanks to my thesis advisor and his experience, thinking the right way to build language systems is we have to learn that knowledge because hand coding it is just too onerous and too impossible to scale.
Okay, I want to stick on that topic and the bridging of machine learning and natural language processing, because there was a time, in the early days where the machine learning community and the natural language processing community, they were basically in different universes. Machine learning was mostly being applied to things like optimization. And as you mentioned, NLP, they were principally using sort of rule-based systems. And you were instrumental in sort of advocating for the use of machine learning on natural language processing problems, which, in hindsight seems very obvious, but at the time was pretty radical. You've already mentioned some of your influences, but what was it that made you confident that machine learning approaches were going to be viable with NLP?
Yeah, so like you said, I actually worked on my thesis in the 80s on this, and so I was sort of born into that idea. But it seemed, it just did intuitively appeal to me that hand coding knowledge, if you've ever sat down and tried to do it yourself,
it's just not going to scale.
And that's what AI students did in the 80s. It's painful, it's laborious. You put one wrong thing in and your system makes stupid mistakes, and then you have to go back and correct it. It's like writing programs, right? There's a debugging process of debugging that knowledge so that it works for the cases you want. It was obvious, I think, that it wouldn't scale. So the idea that machine learning was the right way to build language systems, I think, was always, intuitive and obvious to me. But again, because I grew up with that idea in the academic process. But it really wasn't the symbolic learning systems that I was working on that took over. So in the late 80s, the use of statistical learning in language actually originally came from speech. So in the 1970s, people tried to build something to understand speech, and it really wasn't working very well. And people more from signal processing came in and brought in these ideas of sort of stochastic processes and things like hidden Markov models and statistical methods. We talk about language models now. Language models originated with these things called n-gram language models, where you just gather statistics on how likely does one word follow a previous two words. And they had this thing called trigram models, which is like state-of-the-art technology in the 80s or something, where you say, let's collect a bunch of statistics on how likely each word follows any pair of two previous words. Because just to do trigrams, three-word combinations, you needed quite a bit of data just to get good statistics on that, much less generalizing to
it blows
4
up very
grams
quickly.
or 5 grams. And the amount of data you need is so-called curse of dimensionality, right? The amount of data you need as you can grow that context grows exponentially. So you need so much data just to do trigrams. To go to even bigger context, was sort of infeasible. And so those statistical learning techniques that started in speech started to come into NLP, particularly started with Ken Church did this work on doing part of speech tagging, which is a classic NLP problem where you just want to recognize for each word what the part of speech is. Is it a noun? Is it a verb? Is it a preposition? Is it an adverb? And that actually turns out to be sort of tricky because language is ambiguous. And, the same word could be a noun or it could be a verb depending on the context. So people started developing statistical techniques for that, like hidden Markov models. And then it went to probabilistic context-free grammars, which is taking that to the next level, making a more complicated model of language beyond a finite state machine to a context-free grammar, for those of you who know those concepts from basic computer science. Yeah. And so more statistical learning techniques became very popular in the 90s in natural language processing. A very famous case was IBM developed this system called Candide that did machine translation by training on just huge amounts of so-called parallel text. And they did this between French and English because there happened to be a lot of publicly available electronic data between French and English thanks to the Canadian Parliament proceedings. Because Canada, by law, of course, had to have all their legal documents in both English and French. And this was all publicly available, which having a publicly available IP available text, electronic text in the 90s was not easy.
Right.
So the Canadian government happened to nicely have this nice available resource of a lot of text in both English and French. And that was used, it's called with the Hansards or whatever, was used to train the first statistical machine translation system at IBM in the early 90s. And it was remarkably successful. People were trying to build hand-built rule-based machine translation systems for decades, starting from the 50s. Never really worked that well. But now if we just train on a bunch of parallel text and build a statistical model that recognizes the statistical patterns that connect English and French, it worked remarkably well. And that started this whole so-called statistical revolution in NLP, where all those statistical learning techniques took over. And I was sort of a little bit along for the ride there because I was coming from a slightly different angle of coming more from a symbolic AI background. But then I said, well, these statistical learning techniques are powerful too. And so I drifted more into statistical learning in the 90s.
Right. It reminds me of that old joke, something effective. They were trying to build some NLP system, and the program manager said, every time I fire a linguist, our
that's
performance
Fred
goes up.
Jelinek. He's very famous for this comment.
I love that. I love that one. Okay, so
someone later had wrote a paper titled, "Every time I hire a linguist, my performance goes up."
I know. I don't mean to insult the linguists out there. Okay, that's a perfect segue. I want to talk about the state of NLP now, because we've seen some radical changes. I would argue the most change-rich period of AI within our lifetimes. And we've got things like large language models now, which are, in my opinion, performing what would have been miracles back in the 90s in our perceptions. And they're really based upon what are fairly simple tasks, right? Token distribution prediction. And but falling out of that, we get some pretty amazing emergent behavior. Are you surprised by the performance we're seeing in large language models right now?
Yeah, I think most people in the field, particularly, and came out of the more traditional NLP community, are quite surprised at how well things like large language models based on transformers are working. And I think a lot of that is data. When people talk to me about, well, why is deep learning successful? I always say the first reason is data, data, data. So even in the early 90s, I did experiments comparing symbolic learning techniques to neural net learning techniques in the early 90s and found the algorithm really didn't matter that much. What mattered was how much data you trained these models on. So I was always a believer that data matters more than anything else. And so now, thanks to the internet, we just have incredible amounts of data that these large tech companies can just download off the internet and train these absolutely, at least certainly by my standards, humongous models trained on just incredible amounts of data. And it's amazing, if you train a very large neural network on an incredible amount of data, it is amazing what it can do. And I've been seriously, surprised by the amount of progress in the field in the last couple of years. Just to temper that a bit, though, is, these models still can make dumb mistakes. So one of the lines I use now when I talk about large language models, I came up with a couple of years ago, I said, sometimes large language models surprise you how smart they are, but sometimes they surprise you how stupid they are, because every once in a while, they'll just make the stupidest mistake and say the stupidest thing. Because, these statistical patterns, they work amazingly well in a lot of cases, but sometimes you realize they're not really capturing the deep knowledge of and understanding of the text or the area that humans have. And so they still have serious limitations, and those limitations are just becoming less and less and less prominent, but they're still there.
How do you think that we have pushed this approach as basically as far as we can go, or do you think there's a lot of opportunity still to either increase the size of the models or add more data and get better performance?
So data, I don't know where we get more data at this point.
Right.
My understanding is the companies are basically scraping up every bit of publicly available data on the internet. So I don't see where. So one line that people use is, it's all about scale. And someone publishes paper, scale is all you need. There's this meme because of the original Transformer paper, it's called Attention All You Need. need. It became this meme of something is all you need. So, but I don't believe scale is all you need. Scale is very important. I've been very clear. Data is very important. One other line I always taught my students was there's no data like more data. The more data you can get to train your model, that's always a good thing. But now it seems like we've maxed out on data. But we were talking that, transformers are an interesting model. This idea of self-attention has been amazingly powerful, but they're fundamentally limited because they get a fixed length input window, right, which any language person, is brought up with the idea from Noam Chomsky that language is generative. You can't constrain the length of a sentence. Human sentences can go on forever because you can constantly add new prepositional phrases, or you can constantly increase the length. So having a fixed window that you can process is just, to a computational linguist, is like just crazy limiting. The amazing thing is we've been able to grow these windows. I think the latest, Google Gemini models or something, it's like 1 million tokens.
I think that's right.
Crazy, yeah. Which is shocking to me that you can get a model to work on that length. But just fundamentally, a fixed length window is bad. The other problem with transformers is they grow n squared in that fixed length window because they look at the connection between every possible token within that window, which gives you order n squared, which any computer scientist knows, well, it's not exponential growth, which is the thing any computer scientist really hates. But when you're doing scaling to large amounts of data, it's too bad because n squared grows too fast. You need linear. You need something that can just grow as the computational demands the same size of the data. Something n squared, it quickly becomes intractable. Right. So I think it's hard to scale transformers that give up to more data, more context at this point. I've been amazed it's been growing as much as we can. But we were talking about there are new models out there, like state space models in Mamba that I think hold the promise to actually take us to the next level after this. I think we're sort of plateauing in the transformer area. I always hate to predict plateauing because I've done it before when we were in the LSTM era and we sort of plateaued and then transformers came out and took us to the next level. But I'm hopeful that the next generation of models, if we train on this much data, they'll be even better. So I think, these mistakes that models are making, I think there's room to still improve them further. And I think we need new neural architectures to take us even to the next level.
Yeah, I totally agree with that. We talked about this a little bit, but I too share your enthusiasm around the state space models. And we talked a little bit about even some really recent developments around, there's a new architecture called Jamba that just came out that basically alternates sort of attention blocks with state space blocks. And that could be a way to maybe get around this n squared growth that we're seeing in these fixed context linked windows. Do you have any thoughts on intelligence, like actual intelligence being exhibited within large language models? I know there are some people that think that if you're working with the latest and greatest, let's say, for example, ChatGPT 4, that it by any metric that might have been defined 10 years ago is exhibiting intelligence. And there are other people who just, the stochastic parrot comment. Where do you fall on that spectrum?
Yeah. So, I think people sometimes tend to view intelligence as some sort of binary thing, right, where it's either you have it or you don't. And to me, it's a continuum. And, I think John McCarthy started this idea that even a thermostat is intelligent to some extent. It senses information in the environment and reacts and changes and takes actions based on that information. That is intelligence, just extremely limited. All it can sense is temperature and turn on or off. But, so I think a thermostat is epsilon intelligent. And like I said, I think AI, we've been making progress all along. In the last couple of years, have we made dramatic progress? Did I say to increase the intelligence of these models, remarkably? Absolutely. But I think I've been clear, we're not at the level of, so-called, Turing test level where I would say that, systems are as intelligent as people. But I think how can you deny that these systems aren't intelligent at some reasonable level when they can do the amazing sort of tasks that we've seen? But
I totally agree.
Always be aware that, the next thing they do might be incredibly stupid.
Right. Well, not unlike a human sometimes.
Yeah. People make mistakes also. But I think the types of mistakes that models make and the types of mistakes that people make currently are very different. I could go into a long story about work we did on why question answering why questions about text. But we found that we have stories and have models answer why questions, like, why did John go into the restaurant? And he's like, oh, he was hungry and he needed to eat, and we compare human answers to machine answers from one of these large language models about answering questions about why people do things in stories. And we have humans then rate those answers on usually what's called a Likert scale, 5 points, from really bad to really good. And we eventually found that the best model we could construct and test was getting an average Likert score similar to a human. But then we looked at the breakdown of what those answers look like, and we found a very different distribution. When the model was right, it was really excellent. It produced these beautiful answers that it got more fives. It got more top scores on this Likert scale by human ratings than humans did. On the other hand, it got a number of ones and twos. Humans never got ones and twos. Mm-hmm. Sometimes the machine makes just really dumb answers that a person would never make. So it's not making the same types of mistakes as humans. It's making much dumber mistakes than human makes when it makes a mistake. But when it gets it right, it's even better than human. It's superhuman. So then when you look at the average, it obscures that difference from being very, very smart to being very, very stupid.
Right. Right. Well, I completely share your perspective on intelligence. I don't think it's black and white or binary. I think it's entirely an ingredient, and I do think that these large language models are exhibiting intelligence, not at the human level yet. And the biggest open question to me on that front is how far we can push this. Maybe we've run out of data. Maybe increased parameter count. We'll see diminishing returns. But I'm really, really interested to see just how far we can push it, and just how far we can mimic human intelligence with just such a simple underlying training task. Okay, I want to totally shift focus now. You gave a presentation on the new era of big science AI, where you talked about how with the massive data sets that are being used to train these state-of-the-art models and the enormous hardware costs that go into them, it's very similar to sort of the shift that we've seen in other fields. You can look at astronomy. You used to could build a telescope and grind lens on your own, and now the James Webb Telescope cost I think $10 billion and took a decade or 2 decades to build. We saw the same thing with particle colliders. Within AI now, most of the really, really bleeding edge stuff is being done by private corporations, not government-backed companies. I'd love to just kind of hear your thoughts on that situation.
Yeah. So like you said, I gave a talk of this in my own department at the University of Texas last January, almost a year and a half ago now, when I sensed that this was really becoming an issue. So it's really caused academic research to sort of reorient it, because you can't, do what the big tech companies are doing and build these extremely large models like, ChatGPT or GPT-4. So I think to a certain extent, a lot of the academic work has done more into, I've heard it called analysis instead of synthesis. So instead of trying to build these models, more academic research has just been diving in on understanding these large models that the large tech companies have built. But there are open models too, like Llama, that, thanks to Facebook actually making some of their models public. And those are even easier to analyze because they're more white boxes where you can dive in and actually look at the underlying model compared to a total black box. Like, one joke I always make is OpenAI should be relabeled closed AI because their models are very closed. They're not open. But I think a lot of academic research has gone more to like I said, was just with the work we did on why question answering, exploring what the limits of these models are that are out there, because they do have limits. And it is a useful academic enterprise to understand, okay, where are we right now in AI? It's hard to build new models as a simple little academic team at the universities that have the capabilities of these large models built by the large companies. But there's still a lot of useful work that can be done at universities analyzing and understanding these models better, and also making it clear that they do have limitations and what those limitations are.
Mm-hmm. How do you, as somebody who is teaching actively in artificial intelligence in academia, keep your curriculum up to date? things are moving so quickly. We practitioners who are building, production systems, we are struggling to stay up to date with the latest white papers that are coming out like, a fire hose. What is it like trying to teach in a field moving this fast?
Yeah, so it is very difficult. You have to constantly be updating your classes to keep things up to date. So we were talking, I teach a graduate research seminar on what I call grounded natural language processing, which is connecting language to what I call action perception in the world, connecting language to vision. The big thing is these days is now there's even an acronym for it too, is VLMs, vision language models, where you actually have a model, and GPT-4V is out there now from OpenAI, where you can give it images and language, and it can process both of them. So that's an area that I'm interested in, and it's moving incredibly rapidly. So I have, in a seminar class in graduate school, a lot of times you read academic papers that have come out recently. And now this last year, I had to replace at least a third of the papers I had from the previous year because things had moved so rapidly. I basically felt at least a third of what I covered last year was no longer relevant. I had to replace it with newer stuff. So things are, and it's every day I get all these notifications from Google Scholar about all these papers I should be reading. I just glance down the list and say, well, that looks interesting. Send that to one of my grad students to read because I don't have time to do it.
Oh, that's a great hack. I like that.
Yeah, the joy of being an advisor and having grad students to do most of the work for you.
Yeah.
But yeah, so it is incredibly hard to keep up. And it's also, you get worried about getting scooped because you think you have a new idea. Okay, you do some literature search, you Google, you look on Google Scholar, someone's done, anyone's done this. You start working on it. Then 1 month later, your grad student comes in, I thought to have results, and go, oh God, 3 papers just came out on archive doing exactly what we were trying to do, getting better results than we're getting, we're screwed.
Yeah, yeah. One of my favorite things about the state that we're in right now is there's so much unexplored territory. There are so many opportunities to even take what I think are relatively simple ideas and combine them together and see what you can get out of them. Well, what about the future? Is there anything in particular that you're excited about? You mentioned large vision models and these sort of multi-models. Is that where your interest lies right now, or are there other areas that you're kind of excited about?
Yeah, so I mean, I definitely am still very interested in multimodal models, not just vision and language, but also audio. Now there's a lot of models in action. So now I think I forget what people are calling the acronym, but vision, language and action models, that include like robot actions. And so I think there's lots of capability. Video is another big thing that I think has still a lot of room to make progress because the computational demands of processing video, every image, you get an image every,
30, 60 times a second.
Yeah, incredibly amount of data to process. So I think there's lots of room for progress in multimodal models. And I think that's certainly one very interesting direction that I think has a lot of promise for the near future of being improved.
I totally agree. Do you think the fact that the transform architecture in particular has made it easy for different fields, whether you're like computer vision or you're doing speech recognition or you're doing NLP, the fact that those disparate areas have kind of converged on a common architecture, I think that is part of the acceleration, and it's part of what's making multimodal possible.
Yeah. Yeah, absolutely. So we were talking about, my career path and, like you said, originally language and learning were very different fields. And then they sort of merged in the 90s. Well, for the longest time, language and vision were two completely different fields. I happen to have had exposure to both in grad school. I took a graduate class in computer vision and a graduate class in natural language. Even in the 80s, not many people did that. So I always had a little bit of broader perspective, I think, than a lot of people who were just in language or just in vision. And I always thought these things should be brought together. But it was hard because the two fields were using completely different techniques and made no connection. Now, one of the things I think that is great about the deep learning era is all the fields of AI are using similar, if not the same tools, like transformers, like RNNs, like deep networks. And it allows much more fluid communication of ideas and combining multimodal data in the same model to fuse those things. And I think that has been one of the amazing things. And of course, the application that's become big is generating images and video. We have DALL-E and Sora and these sorts of things. And again, they're not that great if you really dig into them. They really can't generate consistent long videos, say, but there's room for a lot of progress there.
Yeah, and I think Sora, there is generating like up to a minute of video, which is pretty significant jump. But even some of the best videos you see there are
glitches.
There are glitches that
weird,
will come and go.
Weird things, yeah.
But it's still moving at a breakneck pace. You've been working within the field of artificial intelligence for decades. And I remember in the early 2000s when I had completed my graduate degree in AI, and I was talking to somebody who was probably 2005, and I mentioned what I'd done in grad school. And their reaction was literally like, ooh, artificial intelligence. What a bad move. What a waste of time. Was there ever a period during your career where as AI sort of waxed and waned in popularity and research funding where you felt like maybe you had made a mistake, maybe it was too far away in the future to ever be effective in your lifetime?
No, not since 1979. I mean, I guess sometimes I feel like I've been lucky. I gave this talk at the Natural Language Conference in Singapore last December about my career and things like that, and someone talked to me about this sort of issue, and I was like, no, I got excited about AI when I was in high school, and I've never questioned it, and I think I've always realized that it's going to be an important thing that's going to change the world. And I've never questioned that despite all the ups and downs in the field. And I think there are a lot of people like me, right? I mean, there are a lot of people from my generation. I went to AAAI in Vancouver just a couple months ago. Met people I first met 40 years ago at AAAI when I first came, right? And we've all been in the field all that time, optimistic that the field was eventually going to really change the world. And, now we're at a point where it really is, seriously. One thing we didn't talk about is all the negative side effect, too. I mean, we'd had some of our previous conversation about, fake news, Yeah. We didn't really get into all the negative, possible negative impact of AI, which I think is, a serious, interesting topic that, of course, a lot of people are talking about.
What are the things that you're most concerned around? Is it principally like disinformation or other areas?
I think particularly given this election year, right? I think it's something we all have to be concerned about. It was bad enough the last couple of times, right? And now we have much more powerful AI technology that can create amazingly convincing, fake news, personalized to individual people. That could really, potentially have a really negative impact. And our ability to identify whether this is, automatically generated, large language model generated text or not, is already a complicated problem. So I would say immediately, I think the misinformation generation and fake pictures and video and deep fakes and all this stuff probably would be my number one concern for the near future. And we need better techniques for controlling that.
Ray, I've enjoyed this conversation so much. We like to wrap up and ask our guests if they could have AI automate anything in your daily life. Just make something in your daily life better. What would you go for?
That's a good question. I guess just like you said, I get all these notices for all these papers, and there is technology out there that can do summarization and things of that sort. But and I think some people have looked at like personalized summarization, where it's actually, summarize a bunch of documents just for you, right, rather than just for a general audience. And so I think something like that, and again, I think maybe the technology is getting close to the point to do it, that instead of me just having to scan through all these things, is I just got a nice summarized report. Here's what's happened in AI, today that's important for you, that I think you really would like to know about based on your interest and your expertise. And I think that one thing could maybe make my life a little bit easier.
Yeah, I could go for that too. Well, Ray, thank you so much. This was an absolute pleasure and an honor.
Okay, well, it was nice talking to you.
Thank you for listening to Hidden Layers. This series is hosted by Kung Fu AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at kungfu.ai.